Malicious Python libraries and coding agents. Warning: if you've been using coding agents without safeguards, you may already have malicious code in your system. You may need to rewrite in a safe environment. The second part of this blog has information on setting up a safe environment. Gemini prompt. Discuss the existence of malicious Python libraries and the possibility that coding agents will use them. Gemini response. The intersection of open-source software supply chain attacks and autonomous AI coding agents is one of the most pressing frontiers in modern cybersecurity. Here is a breakdown of how malicious Python libraries operate today and the unique risks posed by letting autonomous AI agents write and execute code. The landscape of malicious Python libraries. The Python Package Index, PyPI, is a massive repository of open-source software. Because anyone can upload a package to PyPI, threat actors weaponize it using several distinct vectors. 1. Common attack vectors. Typo squatting, registering names very similar to popular libraries. For example, requests versus requests, or Colorama versus Colorama PKG. Starjacking and social engineering. Attackers create fake packages with documentation copied from legitimate projects to build trust. Dependency hijacking/repo jacking. Gaining access to a legitimate maintainer's account via credential leaks, session hijacking, or CI/CD pipeline compromises to push a malicious update to a trusted, popular package. 2. Execution mechanisms. Malware in Python libraries does not require a user to execute a binary. It can run automatically via import time execution. Malicious code embedded at the top of a _init_init__.py file runs the moment a developer types import package _name. Configuration hooks .pth files. Python automatically processes .pth files when the interpreter starts up. Attackers use this to gain persistence on a machine without the package even being imported. Recent case study, March 2026. The popular Little package, used to unify API calls to OpenAI, Anthropic, etc., fell victim to a supply chain compromise. Attackers hijacked the publishing pipeline and pushed malicious versions 1.82.7 and 1.82.8 to PyPI. The poisoned library was designed to scrape AWS/GCP credentials, SSH keys, and Kubernetes tokens, exfiltrating them before being quarantined by PyPI. The risk of autonomous coding agents. As software engineering moves toward autonomous AI agents like Devin, AutoGPT, or agentic workflows in Cursor and GitHub Copilot, the dynamic of software supply chain security changes dramatically. Here is why coding agents amplify the risk of malicious Python libraries. 1. Hallucinations and phony libraries. LLMs can hallucinate library names that do not exist. If an agent attempts to solve a problem by generating a pip install hallucinated dash package command, an attacker monitoring PyPI can quickly register that hallucinated name and upload a malicious payload. The next time the agent, or a human copy-pasting its code, runs it, they install the attacker's malware. 2. Lack of heuristic skepticism. Humans often look for gut check signals when installing a library. Does this have a README? How many stars does it have on GitHub? When was it published? An autonomous agent, unless explicitly programmed to do so, may not verify these metrics. If it finds a package name that seems to solve its prompt, it will install it programmatically without human oversight. 3. Permission and environment creep. For a coding agent to be useful, it often requires read/write access to a file system, terminal execution rights, and deployment privileges. If an agent installs a malicious library, the malware instantly inherits the agent's broad permissions. This allows automated malware to siphon environment variables, including OpenAI/Anthropic API keys, upload source code to attacker-controlled servers, modify CI/CD deployment files to inject backdoors into production software, defending the agentic future. To safely utilize coding agents without falling victim to poisoned PyPI packages, organizations are shifting towards several defensive paradigms. Sandboxing, running coding agents in strictly isolated containers or micro VMs with no access to host environment variables or sensitive local files. Vetted proxies and mirroring, restricting agents to a private package mirror, like Artifactory or Nexus, that only contains pre-approved scanned libraries. Dependency pinning, forcing agents to use cryptographic hashes, SHAs, for dependencies, rather than pulling the latest version blindly. Age gates, implementing guardrails in package managers, like pip or UV, that block the installation of packages published less than, for example, 24 hours ago. Would you like us to explore how to set up a secure, sandboxed environment for testing local AI coding agents? Setting up a secure environment for AI agents is no longer optional. It's a prerequisite for any developer who doesn't want their API keys or source code leaked by a hallucinated or compromised package. Here is a layered approach to building a blast radius defense for local coding agents. Layer 1. The Virtual Sandbox, Docker. Never run an autonomous agent directly on your host OS. Using a container ensures that even if a malicious library runs rm-rf/ or tries to scan your local network, it is trapped inside a disposable environment. Recommended setup. No root. Run the Docker container as a non-root user. Limited networking. If the agent doesn't need to reach the open web, disable networking or use a firewall to allow only specific domains like pipi.org or api.openai.com. Volume isolation. Do not mount your entire /documents folder. Only mount the specific project directory the agent needs. Layer 2. Package vetting with pip-audit. Before allowing an agent to execute a generated requirements.txt, you can force it through a scanning step. Pip-audit uses the Google-maintained Python advisory database to check for known vulnerabilities. The workflow. Agent generates code and a list of dependencies. A supervisory script runs bash pip-audit-r requirements.txt. If a vulnerability is found, the execution is blocked, and the agent is prompted to find an alternative library. Layer 3. The age gate strategy. Most malicious packages are caught and removed from PyPI within 24 to 48 hours. You can dramatically reduce risk by preventing your agent from installing any package version released in the last few days. You can use tools like UV, a high-performance Python package manager, with specific flags, or a custom wrapper script that checks the PYPIJSON API. Check logic. If open parenthesis current _ time minus package _ release _ time close parenthesis less than 48 _ hours block _ install. Layer 4. Secret management, the honey vault. If an agent installs a malicious library, the first thing the malware will do is run env to find your OpenAI _API _ key, or a WS _ secret _ access _ key. Use a proxy. Instead of giving the agent your real API keys, use a service like LiteLLM Proxy or Helicone. The agent gets a temporary, limited scope key, while your master key stays safely on your host machine. Ephemeral credentials. Use tools like AWS IAM roles for anywhere or tailscale-based identity, so that the credentials inside the sandbox expire every hour. Quick implementation checklist. Component, tool recommendation. Purpose, containerization, Docker/Podman. Prevents host file system access. Package manager, UV or Poetry. Ensures reproducible builds and hash verification. Scanning, pip-audit. Checks for known CVEs in libraries. Environment control, python-.env. Loads only the specific variables needed for the task. Monitoring, snic or socket.dev. Real-time supply chain protection for PIPI. A note on human in the loop. Even with these technical layers, the most effective sandbox is a human in the loop, HITL. Configure your agent to pause and ask for permission before running any pip install command. A quick 5-second glance at a library name can prevent a 5-hour recovery from a security breach. Would you like a sample Docker Compose file to help you spin up a secure testing environment for your next agent experiment? Building a secure harness for a Python-based AI agent is about creating defense in depth. If the agent is tricked into installing a malicious library, the container is the cage that keeps the predator from reaching your personal files. Below is a production-ready Docker Compose.yml and Docker file template designed to isolate an agentic workflow. The agent jail configuration. This setup uses a non-root user, disables automatic network access to your local host, and uses read-only mounts where possible. 1. The Docker file. This file builds the cell for your agent. It pre-installs security auditing tools so they are ready to go. Docker file. Use a slim official Python image. From Python 3.11-slim. Create a non-privileged user. Run group add -ge 1000 agent user && User add -u1000-g agentuser -m agentuser. Hash install system level security tools. Run apt-get update && apt-get install -y -no install recommends /dot curl /dot and nrm-rf /var/lib/apt/list/star dot hash install pip-audit for dependency scanning. Run pip install -no cache -dir pip-audit uv. Hash set the working directory workdir/home/agent user/app. Switch to the non-root user. User agentuser. Default command. Just keep the container alive for the agent to connect. CMD open bracket quote. Sleep quote, comma quote, infinity, quote, close bracket. 2. The Docker Compose file. This orchestrates the environment, ensuring the agent can't see your home network or other local services. YAML, services, AI agent, build, container_name:agent_sandbox. Limit the memory so a malicious loop doesn't crash your PC. Deploy. Resources, limits, memory, 2 gigabytes, volumes. Mount the workspace as read/write for the agent. --home/agentuser/app/workspace. Mount your requirements file as read-only so the agent can't hide its tracks. --/requirements.txt:/home/agentuser/app/requirements.txt:/ro. Environment, hash only pass. Exactly what is needed, never the whole .env. -open AI_API_key equals $. Open brace agent _API_key close brace dot networks. Agent _restricted_net networks. Agent _restricted_net driver bridge. This prevents the container from accessing your local LAN devices, printers, routers. Internal, false. Your execution workflow. Once you have this running, docker-compose-up-d, you should follow this 3-step protocol before letting the agent run any code. Step 1. The audit. Before the agent runs pip install, trigger a scan from your host machine into the container. Bash, docker exec agent _ sandbox pip audit -r requirements.txt. Step 2. The dry run. Have the agent explain why it chose a specific library. If it says, I'm using fast request because it's faster, and you know the standard is requests, stop. This is a classic typo squatting hallmark. Step 3. Minimalist environment variables. Instead of a .env file with your AWS, Stripe, and OpenAI keys, use a proxy key. Recommendation: use a tool like LiteLLM to create a virtual key that has a $5 spend limit. If the agent or a malicious library steals it, your main account remains safe. The golden rule of agent security. Never mount your SSH keys ~/.ssh or your Docker socket /var/run/docker.sock into the agent's container. If an agent has access to your Docker socket, a malicious library can use it to escape the container and gain full control over your entire computer. Would you like a Python script that automates the pip audit check before the agent starts? To make this fully operational, you need a gatekeeper script. This Python script acts as the bridge between your AI agent's desires and the actual execution inside the Docker sandbox. It automatically runs the audit and refuses to proceed if it smells a poisoned library. The gatekeeper.py script. Place this on your host machine. It wraps the Docker command and scans the requirements.txt before allowing the container to install anything. Python. Import subprocess. Import sys. defsecure _install open parenthesis requirements _path equals quote requirements.txt quote close parenthesis print open parenthesis f quote magnifying glass audit scanning open brace requirements _path close brace for malicious packages ... close parenthesis. Run pip-audit inside the container against the requirements file. Audit _cmd equals open bracket dot. Docker. Exec. Agent _sandbox. pip-audit -r. f/home/agent user /app /open brace requirements _path close brace. Try. Result equals subprocess.run open parenthesis audit _cmd comma capture _output equals true comma text equals true comma check equals true close parenthesis print open parenthesis quote check mark audit no known vulnerabilities found quote close parenthesis dot. If audit passes, proceed with installation. Print open parenthesis quote rocket install. Proceeding with installation ... quote close parenthesis. Install _cmd equals open bracket quote docker quote comma quote exec quote comma quote agent _sandbox quote comma quote uv quote comma quote pip quote comma quote install quote comma quote -r quote comma requirements _path close bracket. Subprocess.run open parenthesis install _cmd comma check equals true close parenthesis. Except subprocess dot called process error as print open parenthesis quote cross security alert. Malicious or vulnerable package detected. Quote close parenthesis. Print open parenthesis e.std. OUT. close parenthesis. Print open parenthesis e.stderr close parenthesis. Sayes.exit open parenthesis 1 close parenthesis. If underscore underscore name underscore underscore equals quote underscore underscore main underscore underscore quote colon secure underscore install parens. How the architecture fits together. By combining the Docker isolation with the gatekeeper script, you create a workflow where the agent is never trusting the internet directly. Key security benefits of this setup. Immutability. The agent cannot modify the gatekeeper.py script because it lives outside the container. Resource capping. The deploy.resources.limits in the YAML file prevents a malicious library from launching a fork bomb or a crypto miner that could freeze your host OS network stealth. By using an internal false bridge but not mapping ports, the agent can reach out to get its job done. But external hackers cannot dial in to the container if the library opens a backdoor listener reverse shell. Pro tip: use honey tokens. If you want to be 100% sure the agent or a library isn't misbehaving, place a file named passwords.txt inside the container's workspace with a fake API key inside. Monitor that fake key using a tool like Canary Tokens. If you ever get an email saying that fake key was used, you know a library the agent installed tried to steal your data, and you should kill the container immediately. Do you know that any private information you put into a cloud AI is used to train that AI? A private AI running on your own hardware is the best way to keep your private data private. I can help you set up a private AI on almost any PC or server. Contact me for a free consultation. If you get value from these blogs, please consider joining my Patreon as a member at the $2, $4, or $8 level. There are more than 400 previous blogs on my Patreon page. https://www.patreon.com/Steve Hovland.